Hello, class. This is going to be about the Chapter 4, the first few sections on probability for our EGR 3430 class. So thank you for joining me. I'm in Dallas right now, and I appreciate your flexibility. One of the things I did want to report, and I'm going to send out a class announcement about this as soon as I get a little bit more information, but I want to have a study session where I'm going to be on campus on Saturday morning from 9 to 11 this Saturday morning. So that way I'll find out what location, what computer lab we can get for that. That way we can stay connected and also make sure that we're all making progress here. So I apologize for not being in class this week due to my work schedule and having to travel, but hopefully you can spare some time on Saturday. I'm going to try to make it from 9 to 11. If you want to just come in for a half hour, if you got a question or two, or if you want an hour, if you want to stay the whole period. I don't know who's available and when, but I'm just pretty much making it 2 hours of office hours there at a computer lab so we can work on that, on any questions you might have. So okay, well, let's get into this material. And again, this book really continues to impress me, so I hope you find it the same way. It's kind of hard to get excited about statistics, I know, but it will make a difference in how you look at the world and how you'll be able to be contributing in whatever ventures you're planning to go towards. So first of all, I like the definition of probability. He pretty much lays it out there as a statistical tool, and I think that's a good way to look at it. And it's used to draw conclusions. I got to keep looking at my notes here, so I apologize for that. But used to draw conclusions about sampled populations. There's a lot of new language in this chapter. It's kind of what I've been saying. The math isn't as much of a challenge as just the logic and the terminology that goes along with this logic. So that this kind of keeps going back to my metaphysical, physical type of analogy there, that we're working on our language skills and how we describe data, and more than we are really tackling some complex algorithm and methodology of mathematical complexity. So the one thing that we'll get out of probability is we're going to be able to create what's called probability distributions, and those there's several of them, and depending on the type of data that we're working with, each probability distribution is a good approximation of how we would model that particular circumstance of data that we're looking at. So when we get into it, there's discrete probability distributions, and then there's continuous ones. So that's kind of one breakdown there of just how the division of how we look at data kind of extends from the core part of the data. So we always got to define that core data before we understand what the best way to express that and communicate it and analyze it is with the statistical tools. So these probability distributions will serve as models for discrete random variables. So we'll be talking more about random variables too. So I like the way he breaks it down. Probability is used two different ways. The first is when the population is known, and get that, we're looking at the known population, and we're going to describe the likelihood of observations that we have about a particular sample outcome. So I've got a prop actually this time. Boy, I don't know if you can see that. There we go. I'm looking in the camera here. So again, we know the population, and then we can kind of say, well, what if this sampling was done this way? What's the likelihood we'd see that with this known population? So that's one way we're going to evaluate or utilize probability. And the second way is, like, we don't know this population, but we want to make statements from our sample about the makeup of the population. So that's called statistical inference. So, for example, we get 30 samples and we find out the average is 15, and then based on the standard deviation of those 30 samples with average of 15, we could say with 95% probability the average of the population is between 13 and 17 or something like that. So that's how we're making a statistical inference about the population. So we'll get into that more later, but those are the two things, the two uses of probability that we're really after here. So we got to get to the basics of probability first. So that's kind of the purpose for what we're doing, but there's a lot of different details about probability that we need to cover. So I really encourage you to read this chapter. If you go right into page 128, the toss of a coin is 50-50, and it does a really good job, better than I can really explain it, of showing, well, what happens if that coin is biased, equally likely. I'm sorry, unbiased, which means it's equally likely. Then every time, if you toss the coin 100 times and it's unbiased, you're going to get 50 coin tosses that are head, maybe 51, 52, who knows, and then maybe 50 tails, right? So unbiased coin, you should get that. You certainly wouldn't expect if you tossed an unbiased coin 100 times to get 90 times of a head. So something would be out of balance there. So, and if you think about it, that's really where another purpose here is, if we assume things are randomly distributed and unbiased, but yet we get outcomes that are biased, or I'm sure that exhibit that there's some bias to it, that means there's something beyond what's random going on. So then you've got a special cause. So that's how trends can help us identify if there's something different happening in a process than what's just random, normal statistical variation. So see how that kind of plays. So it's rudimentary if you look at this page 128 example and read through that, but it's real simple, but you're gonna kind of really crystallize that into your memory, because that's what's gonna be a trigger later on to say, hey, something's not right here, something's going on, and it's just, if it was random, it wouldn't be this way. So we got a special cause going on. So good tool to look at there. I do also I don't know if I've ever remember, or if I probably have seen it, but the definition of an experiment is the process by which an observation or measurement is obtained. So it's that real simple. And I really like the way we got some examples here. Recording a test grade. Now, see, this is, again, this terminology. Would you have ever thought recording a test grade is really an experiment? But it is. So measuring daily rainfall. That was more tangible, that, yeah, you're getting a measurement, so that's an experiment. But you really, again, we're taking an instrument and we're using it to estimate our true state of nature. So that's why it's an experiment. It's the process by which an observation or measurement is obtained. Interviewing a householder to obtain his or her opinion. Testing a printed circuit board to determine whether it is a defective product or an acceptable product. See, that's getting more into some practical manufacturing. Tossing a coin and observing the face that appears. So I would keep reading here. Go through this. The simple event is an outcome that is observed on a single repetition of an experiment, and then an event is a collection of simple events. So maybe you like baseball cards, maybe you like stamps, maybe you like to collect even leaves or coins, but here, if you collect simple events, you'll have an event. So again, we're working with new terminology. So we define an event A and B, for example, I'm looking at example 4.1 here. A is observe an odd number, B is observe a number less than 4. So you can identify what the occurrences are for all those simple events, and then come up with what the results are of how many things would happen in those conditions. Mutually exclusive, when one event occurs, others cannot, and vice versa. But you can have not mutually exclusive events when you have two outcomes in common. So, the best way to look at that is using a Venn diagram. So you can see figure 4.1, and hopefully by now you've figured out it helps to follow along in the book. Sorry, I should have mentioned that earlier, but kind of implied there. And the Venn diagram shows you the total sample space. So if you look there, they show you there's event A and event B, and there's six simple events in there. And then it showed A is in the blue, B is in the gray, and then there's two of the simple events that overlap. So you can kind of walk through that and see how that it gives you a visual description of how each one of those events probability exists there. So again, walk through. I think really just read through these and kind of sort them out yourself. Example 4.2, 4.3, 4.4, and then I think this is highly useful. This is actually the technique that finally back in the day helped me understand statistics a lot better through probability with the tree diagram. So that shows you one of the variables is blood type, and looking at figure 4.2 now, and the other variable is RH factor. And you can see that there's 4 different blood types, and each one can have either a positive or negative RH factor. So you end up with 8 different outcomes there. And so if they're all equally, there's an equal chance for all of them, you're going to end up with 1/8, 0.125 probability, or 12.5%, however you want to declare that. And then the total of all those potential outcomes is equal to 1.0. So that's 100%. All potential outcomes are 100%. If there's no potential outcome, if you don't run that, if you don't get the data, then you have 0%, right? So somewhere your event is going to be between 0 and 1 is the convention that's really applied here. Then section 4.3 there, we're looking at relative frequency is the frequency that event is happening divided by the number of potential repetitions that are there of the experiment. So, and then a probability of event is that same equation, the frequency over the number of occurrences, but it takes those number of occurrences to infinity, and so that becomes a probability of that event. So just a little algebra there to kind of jump past the normal difference between the relative frequency and the probability. So kind of one and the same, but just a slight distinction there. So again, read through that. Got more examples on pages 132 and 133. Again, I really think that's something you could go ahead and pursue on your own. I don't think I could say it any better, and I think they're good examples. So, and then on page 134 there, it actually just gives you a summary of kind of a quick method that's going to be used over and over again for the problem set. So, so that's at section 4.4. It says optional. I'm going to go with optional. For now, I don't know that we need to get into permutations and combinations, but I encourage you to read it. This is definitely the You can really solve some interesting problems once you get this mastered. But I'll leave it like onto your own to review that for now. I'll look at the set of problems we have, and maybe if we get further into the class and it looks like it'd really be useful for us to go back and cover this section in more detail, I'll do that. But for now, we just cover that on your own. And with that, I'm gonna pause for now, and I will continue later with another posting, hopefully in a little while, on beginning with chapter 4, with section 4.6, and then I'll round out the chapter there for now. And then we also have another chapter 5 for this week too that I have to finish up. So thanks. As always, get a hold of me via email if we got any questions. I will also be posting some questions that go along with the chapter here within the next couple, probably by Wednesday night, I'll just say. Thank you, sir.